So let's look at the various encoding schemes that people have already designed. So among the digital encoding schemes, one of the simplest encoding scheme we have is called as NRZ, or non-return to zero encoding. Then we have something called NRZI, which is non-return to zero with inversion. Then we have return to zero, which is RZ. Then you have pseudo-ternary encoding. Then we have something called AMI, or alternate mark inversion encoding scheme. Then we have Manchester encoding and differential Manchester encoding. So these are the 7 encoding schemes that we will take a look at now. Let's look at the NRZ first. Now in non-return to zero, it's a very simple encoding scheme. We just represent 0 and 1 by 2 different levels of signals. So let's say 0 is represented by a low level signal and 1 by a high level signal. So now all I need to do is, when I want to transmit a series of 1, 1, 1, 0, 0, 0 or whatever, a 1 is represented by a high level signal, followed that I have another 1 bit, so I continue to maintain it at a high level, another 1 bit, maintain it at a high level. Now I have a 0 to be transmitted, so I switch to a low level signal. Then I have a 0 to be transmitted, again continues at the 0 level, low level signal. Then I have again 0, so low level. Again I have a 1, I go back to high level and so on. So you just keep shifting between a high level and a low level depending on whether you want to transmit a 0 or you want to transmit a 1. A very, very simple signal. The low level signal could be a 0 value signal, high level signal could be a some amplitude A. Okay, this is all that we have when you are looking at non-return to zero encoding scheme. Now we call it non-return to zero because this is very different from a return to zero encoding. When we look at return to zero, you will understand why we refer to this as non-return to zero. So now let's look at the properties of this non-return to zero encoding. In a non-return to zero encoding, a DC component exists. What do I mean by a DC component? I am taking the average of the signal. Let's say I am representing 0 as a 0 volt signal and 1 as a signal with an amplitude of A. So if I take this signal, there is obviously a positive DC component. Now what is the DC component? It is the average value of the signal, right? So if I take this, there will be an average value which is somewhere between 0 and my amplitude A. So this DC component existing is one of the disadvantages of the NRZ encoding. Second thing is, if I have a long transitions of zeros or ones, suppose I am transmitting all zeros, what will happen is I will just have a low signal being transmitted right through. Similarly, if I have a series of ones, I will just have a high signal being transmitted right through, that is, there will be no transitions in the signal. And we have seen that if there are no transitions in the signal, it becomes difficult for synchronizing the clock. So it is not very good for clock synchronization. Third property is that it is also susceptible to noise. So which means the 3 desirable properties that we talked about, all the 3 are missing in the NRZ scheme. It has a DC component, it does not have transitions when you have long runs of zeros and ones. Of course, if you have zeros and ones being transmitted alternately, there will be you will have a transition from 0 to 1, from 1 to 0, 0 to 1, 1 to 0 and so on. But when you have a long series of zeros or ones, you have a problem. And it is susceptible to noise because we are again looking at the amplitude value in order to identify whether it is a 1 or a 0. So it is susceptible to noise. So this is our NRZ. So naturally, because it has so many disadvantages, it is not very suitable for long distance transmission. But it is a very simple encoding scheme. So it is used in places where you do not expect too many errors and you are looking at a very simple mechanism for encoding the data. Okay. So this is used typically in places like magnetic storage, recording and so on. So use a NRZ encoding scheme. The other is the NRZI encoding scheme, which is called non-return to zero with an inversion. So what do we mean by this inversion? So what we do here is, whenever I want to represent a 1, the 1 is represented as a transition at the beginning of an interval. So I have an interval during which 1 is being transmitted. Let's look at this example. I am having 1, 1, 0, 0, 0, 1, 0 being transmitted. So when I have a 1 to be transmitted, I transition from whatever value I was to a high level. Now a second one that needs to be transmitted, I move over to the low level. So remember, I still have 2 levels to represent the different values. I use a high level and a 1 level, but it is not an absolute value that is representing a 0 or a 1, but a transition from a high level to a low level or from low level to a high level that represents a 1. So when I have a transition here, from here it is from high level to low level, this represents that I have a 1 bit over here. Now from 1 to 0, because the 0 that needs to be encoded, I do not have a transition. Again here I do not have a transition, again here I do not have a transition, but now I want to encode a 1, so again have a transition from 0 to 1. So what we do here is you have to look for transitions to find out whether there is a 0 being transmitted or a 1 being transmitted. This is the NRZI scheme. The inversion, the I there stands for inversion, that you can see that once subsequent ones, a 1 following another one will always be inverted. So if this one is high, the next one is low. The next one which occurs over here will be a high level signal. So there's an inversion that takes place on ones, which is why we refer to this as a NRZ-I scheme. Let's look at the advantage of the NRZ-I scheme or the disadvantage of it. Again, it will have a DC component, because if you're looking at, let's say for instance, this is a value of A that's being used over here and a value of minus A or 0 that's being used over here. Depending on the pattern of data you will have a DC component that is present. So there will be a DC component. So that disadvantage remains. But it has better noise immunity, because you're not looking for level values to identify whether it is a 0 or a 1, but you're looking for transitions to identify whether it's a 0 or 1. So a change in signal is what is being used. Whenever we look at change in signals, we refer to that as differential signaling. So differential signaling indicates that I'm looking for a difference in the signal. Earlier my signal was at a particular level. Now my signal is at a different level. Whenever a change occurs, I know that some data is being transmitted. I know it is a 1. When no change occurs, I know that there is a 0 being transmitted. So in that sense, this signal will have a better noise immunity. Of course, if you have noise which causes a transition, then you lose your noise immunity. This is one of the advantages of the NRZ-I scheme. The third is it can lose clock synchronization for long runs of zeros. If you have long runs of ones, remember that every one will give you a transition. But if I have a long run of zeros, then there will be no transitions at all, so you are likely to lose synchronization. So this is what we have with the NRZ-I scheme. Next, if you look at the return to 0 scheme, this is again a very simple encoding scheme. 0 is transmitted as a 0 level signal, 1 is transmitted as a high level signal, but it returns to 0. This is what gives it the name of return to 0. Now you can see how this was different from the NRZ scheme, where a 1 would remain at a high level itself, right? It would not return to 0. So if you look at this signal, suppose I am coding 0, 1, 1, 0, 0, 1, 1. Look at how the signal will look like. 0 will be coded with as just a low level signal. A 1 will be coded as signal which goes high and comes back to 0. Again a 1 goes high, comes back to 0. 0 will be represented as just a low level signal, and then so on. So this again has properties which are very similar to that of the NRZ-I scheme, because if I have a series of ones being transmitted, look at what will happen. I have a transition. Because I have transitions for ones, then you will not lose synchronization when you have this. But if I have a series of zeros being transmission, again you are likely to lose synchronization, and of course it is susceptible to noise, because you are looking for levels, either it is a high level or it is at a low level. So since you are looking for a level, naturally it becomes susceptible to noise. So this is what we have with the return to 0 encoding. Now in order to take care of these problems that you have with these NRZ and RZ techniques, we have what are called as pseudo-ternary and AMI encoding schemes, which are referred to as bipolar encoding schemes. What do you mean bipolar? Bipolar indicates that you use both positive values and negative values to encode your signal. So now what happens is, let's look at what the pseudo-ternary does. It uses 3 different levels to encode the signals. That is, a 1 is encoded as a no line signal. Okay, 1 is basically at a 0 level. A 0 is encoded either as at a positive level or at a negative level, depending on whether it occurs following a 0. That is, every alternate 0 is represented either as a positive signal or a negative signal. So let's look at this particular sequence: 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1. So a 0, assuming that my preceding bit had a 0 had a negative voltage, will start with a positive voltage here. Then I have a 1, so it is represented as a no line signal, 0 voltage. Next 0 is represented as a negative pulse, negative level signal. Next 0 is represented as a positive level signal. Then I have 2 1s which are represented as 0 level signals. Again I have a 0, so a negative level signal. Another 0, positive level. Another 0, negative level. 1 and 1, again 0 level signals. So you can see what happens over here. You can see that there are enough number of transitions that occur, okay, except when you have a series of ones. If you have a series of zeros, I will have enough number of transitions. And if you look at the DC component, the DC component here will be 0. Why would that be 0? Because whenever I have a 0 followed by another 0, the first would have been a positive pulse, the next would have been a negative pulse. Next will be a positive pulse, next will be a negative pulse. So on an average, all positive pulses will cancel out the negative pulses, and the DC level will become 0. So this is one of the major advantage of this pseudo-ternary scheme. A similar scheme is the bipolar AMI scheme, which is called alternate mark inversion, which is just the reverse of the pseudo-ternary scheme. Here what you do is 0 is represented as no line signal and 1 is represented as either a positive or negative level, alternative for successive ones. So look at the same sequence here. I have 0 1 0 0 1 1 0 0 0 1 1. So 0 represented as a no line signal, 1 is represented as a positive value, this being the first signal, assuming the previous value was negative. So this is a positive value signal. Then 0, 0, no line signals, 0 value. Next one will be a negative level signal. Next one positive. Again I have three zeros, which is therefore it will be at no line signal. Next one, the previous one was a positive, so this will be negative. Next one will be positive, and so on. You can just see pseudo-ternary and bipolar AMI, just the reverse of each other in the sense that in one case zeros are coded using 2 levels, in the other case 1 is coded using 2 levels. It is called as alternate mark inversion, because mark basically refers to 1. It is the ones that are being inverted in this particular scheme. Now if you look at the properties of both these, bipolar AMI and pseudo-ternary, they have similar properties. One is, of course, as we saw, there is no DC component because the positive pulses cancel out the negative pulses. The second interesting property is that it has an error detection capability. What do you mean by error detection capability? You expect that when I have a 1 followed by another 1, naturally if this was positive, I should have a negative pulse following it. I cannot have 2 positive pulses occurring one after another. Suppose I had a positive pulse here and I had another positive pulse over here, I know that something is wrong in the encoding. I will actually be able to identify that there is a bit error that has occurred. That is one thing. Third thing is, with respect to synchronization, you could lose synchronization for a long run of zeros in the case of bipolar AMI, and in the case of pseudo-ternary encoding, if you have a long run of ones, then you may lose encoding. You may lose the synchronization because there will be no transitions. So what is normally done is when you use bipolar AMI or pseudo-ternary encoding, we use some kind of scrambling techniques to overcome this property, this problem. Okay, so this is one thing we have. The next encoding scheme that we have is a Manchester encoding scheme. This is a very interesting encoding scheme. What we do here is you always make sure that there is a transition for every single bit that is transmitted. So which means we want to make sure that clock synchronization is never a problem. So always there is a transition. So that is, a 0 is a transition from high to low in the middle of the interval, and 1 is a transition from low to high in the middle of the interval. So look at this particular sequence of bits that you have. I have a 0 being transmitted, so I have a transition like this. It's high followed by a low. Then I have a 1, so I have a low followed by a high. Then I have a 1 again, so again it's a low to high transition. 1 again, so a low to high transition. 1 again, low to high transition. Now I have a 0, so this will now be a high to low transition. 1 again, so this is a low to high transition. So by looking at the middle of the pulse, looking at whether it is going from high to low or low to high, you can identify whether it is a 0 or a 1. Very interesting property, because you have absolute clock synchronization, because for every bit that is transmitted there is a transition available, can be used for synchronizing the clock at the 2 ends. And if you look at this is a positive value and this is a negative value, the DC component is also 0. So that is also another very interesting property of the Manchester encoding. So if you look at the advantages, as we just saw, good clock synchronization, good noise immunity, because again we are looking for transitions, not absolute levels, and there is no DC component. So very good in terms of all these things, but there is a small disadvantage over here. What happens if by mistake the 2 levels were just interchanged? Okay, that is, you had suppose you had 2 leads which are connecting these 2 signal from one end to the other end, and the 2 leads just happen to be converted in a reverse fashion. What will happen is all your highs will appear as lows, all the lows will appear as highs. So which means when you had a high to low transition, it will appear at the other end as a low to high transition. So a 1 on the other side will be interpreted as a 0, a 0 will be interpreted as a 1, so you will get complete reversal of the data that was transmitted. This is one of the problems that you have with the Manchester encoding. To overcome this, we have another encoding scheme called the differential Manchester encoding, which is again similar to the Manchester encoding, but uses again that differential property. Remember what we talked about differential property. Differential always means that you are looking for some difference, not absolute value but a difference. So look at what happens over here. So here in differential Manchester encoding, you always have a transition at the middle of the interval, but a 0 is indicated by a transition at the beginning of the interval and 1 is indicated by no transition at the beginning of the interval. So let's look at what we have. So I have a 0, so I have a transition at the beginning, middle there is always a transition, again another 0, so I have a transition at the beginning of the interval, middle there is always a transition, and so on. Now I have a 1 to be transmitted. Look at this point here. Here there is no transition at the beginning of the interval, there is only a transition at the middle of the interval. So the middle transitions can be used to synchronize the clocks, and presence or absence of a transition at the beginning of the interval can be used to identify a 0 or a 1. So this has all the advantages of Manchester encoding, plus it also takes care of the disadvantage which is there in the Manchester encoding. So very popular encoding scheme. The only disadvantage that the Manchester and the differential Manchester encodings have is that they require twice the baud rate as the bit rate, because there will be 2 transitions that you have for every bit that is encoded. That is the only disadvantage. Otherwise these are 2 very popular encoding schemes. Okay. This is just a quick look at the frequency response of the different encoding schemes. We can see that NRZ-I and NRZ, they have a DC component, so it kind of goes like this, and all of the other encoding schemes have pretty good frequency properties except the Manchester encoding, which requires a higher bandwidth, because I just told you the baud rate will be twice this.